everyone. My name is Lin Kailong. I'm a student of Guangdong University of Technology. Today, I will be presenting our papers Unrolling Ring Guide Detail Recovery Network for Single Image Deraining. At first, we want to talk about the test we are going to solve. Single image deraining is a branch of image denoising problem. And thanks to the repeat development of deep learning, single image deraining test has progressed significantly. It, however, remains a difficult test with some challenges as we list here. The first is that ring state of different shapes, size, and directions obscure image background, so the test modeling and processing is difficult. The removal of ring state while retaining most of detail in a single image is a challenging task. And third, the image degradation caused by ring state limited the performance of many outdoor computer vision systems. Thus, the research of single image deraining algorithm is of great significance and valuable. Generally, the existing single-image deraining methods can be roughly classified into two categories: optimization-based methods and deep learning-based methods. The optimization-based methods based on imaging models. Handcraft priors are enforced on the ring and background image layer to build an optimization model. Then different algorithms are developed to pursue the minimization of optimization. Typical optimization-based deraining methods include image decomposition, sparse coding, Gaussian mixture model. However, most subjective hyperparameters work only for specific ring form and are always inapplicable for real-world ring image. Also, it takes a lot of time to perform a complex optimization process. Recently, the emergence of deep learning has led to the development of variety network-based approach. These methods are based on data-driven, with well-designed networks and appropriate loss function. Numerous training pairs are used to learn mapping from the ring images to clean images directly or progressively. To enhance the performance of the network, some well-designed modules are introduced to the architecture, such as dilated convolutions, residual block, dense block, attentional mechanisms, and to reduce the dependence on training data. Certain state architectures are based on additional ring or image assumptions, like GAN and semi-supervised learning. But many of the learning-based methods cause detail loss because of under-deraining or over-deraining, and this leads to the visual artifacts. The original observation model is often ignored or neglected, rendering the reconstruction unreliable and questionable. And the image priors are often ignored in the deep learning-based ring removal methods. To address the formation issues, we propose a novel unrolling ring guide detail recovery networks named URDIN for single image deraining. According to the altering direction methods of multiplier technique, the proposed URDIM unrolls a single image deraining test into two subproblems: ring extraction and detail recovery. Ring or image pairs are implicitly captured from the data by their corresponding subnetwork structure. As shown in the picture, the subnetwork context aggregation attentional network is introduced to fully exploit global high-level semantic information, which help to extract ring accurately. And the subnetwork background detail recovery network is designed to recover the texture detail loss due to under or over deraining. Next, we will go into more detail of these two structures. First is the context aggregation attention network. It mainly consists of three parts. The first part is a simple convolution block and a channel attention block for obtaining the shallow feature. And then we could say 7 multi-scale dilated channel attention block named MDCB in the second part. The pictures on the right shows the structure of MDCAB. The dilated convolutions enlarge the receiver field with a number of parameters unchanged, and channel attention can adaptively best utilize feature channel-wise attention information. The process can be expressed by these two formulas. The O is represent for the observed image, and the B is a background. R is the ring seek, and these are to the powers of t plus 1 represent for the uh, ring seek we extracted in this stage. The O minus B represent the input of the network, and the WCAM represents the parameters to be learned. Here comes to the background detail recovery network. Based on the observation that the most discrete areas of background image tend to be the most ring crop regions. So the extracted ring is utilized as an independent clue to guide the detail recoveries. And following a convolution and a channel attention block as before to obtain the shallow feature, then with a simple encoder-decoder is introduced to recover the background. The process is expressed by these two formulae, where BDRM denotes the background detail recovery network, and O minus R to the powers of t plus 1 denotes the input of the network. And the second sentence in these formulas, this second R to the powers of t plus 1 serves as a clue to guide the detail recovery, and WBDRM is the parameters to be learned. In this study, we introduced three types of loss function to regularize network chaining. They respectively are negative structure similarity loss, Charbonnier loss on the image field, and on gradient map. In context aggregation attention networks, we use negative SSM loss to constrain the ring we extracted, and in the background detail recovery network, we constrain the output recovered background to be as close to the ground truth background, with negative SSM loss and the Charbonnier loss on image field and on gradient map. The final loss function is defined on two subnetworks. That means that the total loss is computed by the loss of CAAM plus loss of BDRM. And to demonstrate the performance of our proposed method, the URDRM is evaluated on three synthetic datasets: ring 100L, ring 100H, ring 800, and was compared with 10 state-of-the-art methods. And this table shows the quantity comparisons. We can see that the proposed URDRM achieves significantly competitive performance on all datasets compared to the other state-of-the-art method. And to visually demonstrate the performance of proposed method, here we provide the deraining pictures obtained by using the various methods on both synthetic ring image and on real-world ring image. In Ablation Study, we evaluate the effect of four key components of the proposed URDRM by removing them or replacing them. These four components respectively are the multi-scale dilated convolution, named MD, and channel attention, named CA, and ring attention, named RA. The BDRM is the background detail recovery network. The table summarizes the effect of these four components, and the result shows that the URDRM, which combines MD and CA, achieves better performance than the variants that use only MD or CA. And the direct application of BDRM without ring attention in the second stage can compromise the network performance. However, the introduction of an ring attention mat as a clue to guided data recovery can significantly improve the performance. And that's all. Thank you for your attention.